Hi everyone. Today I'd like to talk about how we can change brain activity without surgery or drugs. But first, I think it's important that we understand kind of the immense complexity and beauty of our brains. So when you look at a cartoon image of a brain, it looks like this harmless, squishy pink blob. And it's hard to imagine that inside there is kind of most of everything that makes us us, keeps us alive, and gives us our perceptions of reality. But our brains are actually made up of this really dense network of cells, all interconnected and working together. So this is a section of mouse brain that's about the size of a grain of sand. And the coloured blobs you can see are cell bodies, and you can kind of see the wiring between them. The yellow dots that are coming across are synapses, so that's where the cells are connected and where they're communicating to each other. And kind of what this illustrates is that even in something the size of a grain of sand, there's this incredibly dense network of cells. And it's so dense, in fact, that if you took every cell in the human brain and you made it the size of a marble, you could fill an entire Olympic swimming pool, 50 metres long and 25 metres wide, and about 200 more of them as well. So if anyone ever calls you dense, please know that that's a good thing. So with something so complex, it's not surprising that sometimes things don't go quite as planned. So whether that's through mental health disorders like depression or anxiety, diseases like Parkinson's or Alzheimer's, or other conditions like stroke and chronic pain. As much as I love our squishy pink blob, I think it's really responsible for so much harm. And in fact, if you take the total economic cost between 2010 and 2030 for the harm that's caused by mental health disorders, it's estimated to be around $16.1 trillion. So that's the total kind of lost economic output that we've lost because of mental health disorders. But thankfully, we have some amazing technologies that we're currently using to change brain activity and modulate some of these diseases. So pharmaceuticals, things like antidepressants, are being used to help millions of people manage their symptoms of depression. And implanted devices like deep brain stimulation are also used now routinely for Parkinson's patients. So these devices are implanted in our brains, and for Parkinson's patients, they can help affects their symptoms, so reduce their tremor and things like that. And while these are amazing, there are some issues with them. So pharmaceuticals are really expensive to develop. They're in excess of $1 billion in 10 years per drug. And what's worse is they're actually getting more and more expensive over time. And then with implantable devices, the kind of concern with those is if we're going to scale them up to the many millions or perhaps billions of people that are suffering from some sort of condition with their brain, there's a small but real risk of infection that you'd have to deal with. And also they require talented surgeons to implant them. So scaling them to the size of the challenge is a real problem. So today I'd like to talk about a range of approaches that can allow us to change brain activity without surgery or drugs. One of them is electrical stimulation. So this is where we put electrodes on the scalp and we run electricity between one electrode into the other. And that sounds quite extreme, but we only use, we use less electricity than what a phone charger uses, so it's not quite as extreme as it sounds. Most of the electricity passes from one electrode to the other and kind of stays in the surface in our scalp and causes maybe a mild tingling sensation. But some of it does manage to reach the brain. It can be just enough to encourage or discourage brain activity as we wish. And this technology is just reaching the stage now where it's starting to be used clinically. So the NHS is trialling this for use in treating depression at home, for example. Another technology is ultrasound. So this is what we're working with here at Oxford. And this ultrasound is just sound, but at a much higher frequency than what we can hear. And it turns out that ultrasound has this amazing ability to be focused through the skull, so you can cause high pressure regions where you want, even deep in the brain, without affecting the kind of intervening tissue. And it can also be focused to really small areas, so we can focus it with sub-centimetre accuracy. And so for us, that's really exciting because unlike with electrical stimulation, which is typically only active on kind of the outer regions of the brain, this allows us to target deeper brain regions. And then finally, we've got magnetic stimulation. So this is kind of the most mature technology out of the three. And it was it works through an electromagnet that's placed on the scalp, and strong pulses of electricity are put through that electromagnet, which then creates a magnetic field, which then induces an electric field in the brain. And it can actually produce an electric field that's about 100 times stronger than what you can generate from electrical stimulation, how that's typically done. It's so strong, in fact, that if you put the electromagnet over your motor cortex, the part of your brain that controls your movement, it can cause your muscles to twitch. And this was first approved for use in depression in the US in 2008, and it's also used for conditions like OCD. So you might be looking at these and thinking, they sound great, but why don't we see them everywhere in healthcare? If you've ever gone to the doctors for a range of conditions that's to do with the brain, it's very unlikely that they will have prescribed any of these things in the first instance. And there's a few key reasons for this, which I'll just go over now. So one of them is that all of our brains and our heads are very different. So without looking at anyone in particular, some of you have big heads, some of you are a bit older, no offense. And what this means is that if we're applying electricity to the scalp and trying to reach the brain, if you've got a bigger head, less electricity is likely to reach your brain. If you're older, then your brain shrinks, and then that might mean that it responds differently to stimulation. And so we've got this problem where if you have a group of patients come in for a study and you give 100 people the same amount of stimulation, they all actually end up with very different doses reaching their brain, and some people actually get, say, twice the electricity reaching their brain as others when you're doing electrical stimulation. And so the way that you typically can solve this is you take every person, you put them through an MRI scanner, and that gives you that kind of structural image of their head and their brain. And then you can use that structural image to inform a simulation to find out how much electricity will reach their individual brain, and then try and tune the dose for them. But there's a bit of an issue with this, and that's that it's expensive. Electrical stimulation is kind of meant to be cheap. It can cost less than £100 to build one of these devices. But if you're having every single patient have to come in for an MRI scan, then that's kind of a real barrier for accessibility. So some of the previous research I've done is addressing this challenge without an MRI scan. So instead, we trained a series of algorithms that use your head circumference, your age, your BMI, and your sex, and try to use that to estimate the dose that each individual would need. And while it's not as good as an MRI scanner, we can only get to up to kind of half of the ability to explain the variability across the population. We hope that it's kind of a first step to addressing this challenge of accessible dose control with electrical stimulation. Another reason why we don't see non-invasive brain stimulation everywhere is that we don't fully understand how the brain responds to these different forms of stimulation. So that's particularly the case for ultrasound, as it's quite a new technique. So what we're working on here at the moment is a study where we have enrolled Parkinson's patients. And these Parkinson's patients already have these deep brain stimulation electrodes implanted. And they're there purely for clinical reasons to manage the symptoms of Parkinson's. But the modern version of these devices not only stimulate electrically, but they can also read electrically. So we can read the brain activity deep in the brain in humans, which for us is really exciting. So we want to understand how is the brain responding to ultrasound, and possibly how can we kind of optimize how we're applying the ultrasound going forwards as well. Yeah, that's the study that we're doing at the moment. The human brain is incredibly complex, and I'm not suggesting that non-invasive brain stimulation is going to solve all of our problems. We'll always need surgery and drugs for different conditions, and perhaps the kind of most exciting applications will be when we combine these things together. But what I hope I put across is that non-invasive brain stimulation, these techniques, are kind of an exciting set of tools that are potentially very accessible and scalable, and they'll kind of allow us to change brain activity. And before I finish, I'd like to leave with one more thing, which is that these technologies don't have to just be used for clinical conditions. They can also be used to enhance the activity of healthy individuals, whether that's through attention span, memory, or other things like this. And while the research in this area is kind of fairly nascent, there's a long way to go. I think it's worth considering the impact it would have on our quality of life and on the productivity of our economies as a whole if we had this control over our brains. So yeah, I think it's something to consider in the break or on the way home. If you could have the ability to control your brain like this, what would you like to control? Thank you.